Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process. Enthusiasm provides momentum to the mind of human being to express inner potentiality. So, if you recall, in the till now we have discussed certain requisites for learning the fundamental of combustion. As you know that combustion is basically a multidisciplinary field, right? And therefore, we need to really recall and also relearn some of the things which are very important. For example, we have already looked at the thermodynamics related to combustion, so also the chemical kinetics, right? And today we will be discussing about physics of combustion, right? And that is related to basically there will be transport of the mass, momentum and also the heat transfer, because heat being generated during combustion and that has to be transferred, and that heat transfer makes the combustion process to be self-sustained, right? We will, as you go along, we will see how it is this heat transfer plays an important role for making the combustion process to be self-sustained. And there will be, of course, the mass transfer will be taking place, and we will be looking at the fluid mechanics. If you look at for this transport of energy, momentum and mass, right, what are the driving forces? There should be some driving forces, isn't it? Because suppose you are coming to the class to attend because your driving force to learn. Of course, you are taking a degree, driving force is to get a job, right? So, of course, nowadays, but not knowledge. But similarly, always anything you do for a human being, it is the desire to do is the driving force, isn't it? Anything. So, therefore, what are the driving forces, let us say for mass, like transfer, what will be the driving forces? And there will be also momentum transfer, what will be driving forces? For let us say heat transfer, what will be driving forces, right? And when you talk about the certain transport phenomena, right, the driving forces is important. For example, you are flying from let us say Kanpur to Delhi, okay, then there will be a driver which will take you. A driver means maybe in the train driver, or if you are going by flight, then it will be your captain, right? So, he will be taking you one place to another, right? So, similarly for this mass, momentum and energy, there will be some kind of driver or driving force, what we call, and something has to be driven, like those are transported quantity, right? Quantity will be mass, energy and the momentum, right? And there will be some relationship between both, right? And that we call it governing laws, but in some places you may find constitutive relationship or laws, sometimes people call. So, if you look at for species to transport, like basically mass will be transported through species, right? And there is a concentration gradient, right, we call Fick's law of diffusion. And for momentum to be transported, there will be pressure gradient in the fluid mechanics, but here we will be looking at it a little differently, right, and that is Newton's laws of viscosity, right. And here of course we will be making certain thing to move, and that will be coming under the momentum, because what is pressure? Pressure is basically rate of change of momentum per unit area, right. And for energy transport there will be what you call the temperature gradient which will be driving force, and that constitutive law is known as Fourier's law of heat conduction, right. There will be conduction which will be there. And let us look at basically two stationary plate we are considering, and in which there might be some kind of fluid, let us say air is there, right. Okay. It can be water, it can be any other fluid, right, let us say, and one plate is fixed, right, and the distance between two plates is y we are considering, and there is a stationary plate, and if I say this is basically in x direction and this is y direction, right, and this plate will be suddenly will be given a velocity, let us say Vx, this velocity is Vx, the plate is moving at velocity Vx and fixed plate is not moving, it is remaining fixed. So what will happen, that whatever the fluid will be adjacent to this layer, it will be moving with almost similar velocity, maybe little bit lower, but almost very adjacent to the plate, right. And as the time will progress, then velocity will be basically will be coming decreasing, because impulsivity is being started, like it will be at t is greater than 1, the velocity profile will be like that. But if the time goes on increasing, what will happen, this will be like this as the time is increasing, right. And when time is like reach a steady state, if the a lot of time being elapsed, so then what will happen, it will be reaching a steady state. So you will get a velocity profile like this, right, where at of course this at this surface what will happen, this Vx is basically 0, and in this case of course it is whatever the velocity you have given, and that is constant, this velocity, the plate is moving at a constant velocity, right. Okay. Now if you look at, there is a what you call shear stress, which is nothing but force per unit area which will be acting on this plate, right. And what will it be, I mean if you conduct this experiment, you will find that that is proportional to what, this shear stress will be proportional to velocity, not viscosity, Vx, right, and it will be inversely proportional to the distance y, right. If you look at this is y, that will be inversely proportional. So, and of course this thing I have already talked about it, fluid near the upper plate and gains momentum, and this momentum will be transferred to adjacent fluid layer, right. And keep in mind that these fluid layers we are assuming to be laminar, layer by layer, it is not that we are considering turbulent, right, no. So as a result, then what will happen, there will be shearing of fluid element will be taking, because one is moving at a higher velocity, other is lower velocity, so there will be shear force, right. This velocity is higher and this is lower, so therefore fluid element will be experiencing the shear force. And when the T attains this thing, this shear force basically proportional to the Vx and inversely proportional to the y, right. And if we look at, I can write down here, that is basically Vx, where is this Vx, because this is changing Vx at this point, and this is of course distance y, right, Vx, and here at this point when this will be 0, y is equal to basically y, divided by, and when the Vx, this will be 0 minus y, right. And I can also write down in terms of basically is proportional to dVx by dy, right. I can write down, and this will be having a minus sign, right. So, therefore, I can write down Tyx is equal to minus mu dVx by dy, and this minus sign indicates what? It indicates basically momentum flux, the decreasing with the velocity, right, being transferred, right. So, this mu is basically known as dynamic viscosity, right, and this is law is known as the law of Newton's law of viscosity, right. So, Newton law of viscosity, as I told, is basically is Newton law of viscosity tau Yx. What is the meaning of Yx? Is basically the shear stress along the x direction and in the due to the y momentum flux, right, momentum transfer, right. And if you look at this mu is basically, if I will not consider the magnitude, tau Yx dVx by dy, right. And if you look at unit wise, what will be unit? Tau Yx will be nothing but force per unit area, right, and that will be Newton per meter square, right, and this will be meter per second and divided by meter, right. So, this unit will be basically Newton second meter square, right. This will be meter square, because this will be cancel it out and this will be meter square. And as I told, this is basically the dynamic viscosity, and dVx by dy is shear strain rate in a, of course, with a negative sign, right, and this is acting in the direction of decreasing velocity. This momentum flux is acting in the direction of decreasing velocity. In other words, a momentum transfer takes place from region of higher velocity to the lower velocity, right. And the viscosity for gases basically independent of pressure, and it will be dependent on temperature. It goes by tau is proportional to temperature power to the 0.7, that we will see how it is. Of course, this is from the experimental side for these gases, and viscosity of liquid decreases with increase in temperature. This is just other way around, right. And see these things, the fluid which govern this Newton's law of viscosity is known as the Newtonian fluids. Most of the gases and liquids which generally follow the Newtonian fluid, but there might be some other fluids which does not follow this constitutive relationship between the shear stress and the velocity gradient, right, and that is known as non-Newtonian fluids. You might be aware that some of the, like your toothpaste or the fluid, that is also a fluid, or gel, or your what you call honey, and some viscous liquid does not follow the Newtonian fluid, because this is a layer by layer, that does not really come into, and there will be, and this is we assume a linear change in the velocity profile kind of things, that is not. Now, let us look at this tau Yx. I can write down basically minus mu by rho. I can write down this rho Vx by dy, and this rho Vx in this relationship, what is that? This is basically momentum flux, right, momentum flux, isn't it? and this is and this one we call it as a what we call nu, then this nu minus nu d rho v x by dou y, and nu is basically momentum diffusivity, right, and we also call it basically kinematic viscosity, right, and whose units is happens to be what? If you look at this is Newton second meter square into what you call rho is basically kg per meter cube. So, that if you cancel it out kind of things here, and Newton for that you put that kg meter per second square, you will find that this will be meter square second, right, the unit will be meter square per second. And keep this in mind, momentum diffusivity, because we will be trying to relate this with the other constitutive equation, and as I told, rho Vx is nothing but here momentum flux, right. And we are now armed with how to handle this, what you call viscous, relate this shear stress with the velocity gradient, and we have come up with a property viscosity, and keep in mind this will be dependent on the kinds of molecules you are handling and other things. But question arises how you will determine mu. One way of doing is that you will conduct experiments and find it out, right. But however, that will maybe with the different temperatures, right, and other things, because particularly for gases it is dependent on temperatures, right. Therefore, we need to look at how to handle this viscosity in the combustion problems, because temperature will be changing, right. So, we will see that how we will have to do that maybe little later on. Now, let us look at the problem of heat conduction. We will consider in the similar fashion. Let us say that two plates are there, one plate is having a temperature T naught. See, if you look at this is a temperature T naught, of course to start with all will be at temperature T naught, and there will be uniform temperature here, and let us say it contains some air, right. For the simplicity I can take oxygen, I can take helium, any other gas or any other liquid for conducting experiment, and let us say that this what you call plate 1 also at these regions will be at temperature of uniform, maybe some uniform temperature of the ambient temperature T naught, whatever it is, and suddenly the plate 1 is heated to temperature T1, this became hot plate, right, T1. So, what will happen? It will be temperature will be very high here, and then it will be lower when the T is greater than 0, right, and because the temperature T1 is greater than T naught, that is the cold plate, and this is your hot plate, and as the time passes, then what will happen? This temperature profile will be changing, and then after that it will be having certain kind of temperature profile kind of things, right. It will be at certain temperature, right. This temperature of course is having some finite T naught, and this is your T1. So, will be maintained at that. So, if you look at I mean like in the upper plate maintained at the high temperature. So, therefore, heat transfer to the fluid in the vicinity of the plate. Keep in mind that there is no convection, there is no flow, only the fluid is stationary, right, on the molecular interaction is taking place, right. And then as a due to this temperature, the molecules will be moving at a little higher velocity in the molecular sense, and it will be also due to vibrations, right, and particularly the vibration of the molecule that makes this heat to transfer through that process, and heat transfer takes place between adjacent molecules, and over a period of time the temperature attains a steady state, and this heat flux is basically proportional to the temperature difference, right, and inversely proportional to the distance y between this plate, right, and this is of course y distance, and keep in mind that we are basically this is the x direction, we are using the same coordinate system, right, and if you look at this, basically Q flux, I mean this I can derive from very easily, like if I consider Q flux is, as I told, like Q flux will be proportional to the temperature difference, that is T 1 minus T naught divided by the y, and is proportional to T 1 minus T naught divided by 0 minus y, right, because this is when T is 0, this is y, and this is proportional to your dt by dy, and K is nothing but your thermal conductivity, right, the K is thermal conductivity, and I can write down this as basically Q dash is equal to minus K by rho Cp, and I can write down rho Cpt by dy, and this is minus alpha, we call it thermal diffusivity, into do rho Cpt by dy, and this alpha is thermal diffusivity. And the unit, if you look at, this is also similar to that of your momentum diffusivity, or the what you call kinematic viscosity, right, and this is unit is meter square per second, right, and keep in mind that this I have used Cp, right, to consistent with the textbook whatever, but however we can consider this as a Cv. Why? Because this is basically the there is no motion, right, there is no motion as such, it is basically internal energy due to that which will be happening. So, I can consider as a Cv, because this is the heat conduction is taking place due to molecular motion. So, I will be using Cv for that, are you getting? Then when I am using this Cv, this will be not enthalpy, right, Cpt, if you look at, it will be basically internal energy, that you keep in mind, right. So, Ka, the thermal conductivity is basically function of temperature and species, right. It will be dependent on the species also, whether bimolecular or a monoatomic or a or a polyatomic or a diatomic molecules, that depends on. So, Ki, if you look at, it is a watt meter per Kelvin, that is the unit of thermal conductivity. I is the ith species, and I can write a basically a empirical relationship, a polynomial, C naught plus C1 t plus C2 t square plus C3 t cube and C4 t 4, and some people go for higher order also, right. It is not that only this, and keep in mind that this coefficient which I have shown here for several species, some of them as given here, you can use this thing, and this will be valid for certain temperature range, okay. It is not that it will be valid from 300 Kelvin to the 5000, no, right. Generally it goes for 300 to 1500 and 1500 2500, some other different coefficient will be using, right. So, these are the things one can use for the what you call your calculation, particularly when you are doing computational fluid dynamics, right. So, these are the things, of course, the thermal conductivity which we had used in our computation. I have shown here that this with respect to temperature, like 1 is C7S16 and of course 2 is C10S22, and then of course these are the like various spaces, like 3 is O2 here, this is your basically O2, and 4 is CO2 and this is nitrogen, right, 6 is nitrogen. So, if you look at this is basically how the thermal conductivity is also changing with respect to temperature. If you won't take care of the at certain temperature here calculation unless you won't take care of temperature effect in the calculation of thermal conductivity, then there will be lot of problem, right. So, your estimation won't be right one. So, therefore, you need to look at these things, and of course, like on certain hand calculation we may take some average values, like the way we handle spaces for calculating adiabatic temperature. But however, for the proper estimation, you need to take care of the temperature effect, not average at each locations, because in a flame or some other thing temperature will be changing, it is not that remaining constant, okay. So, therefore, one has to worry about it, and with this we will stop over here, and then we will look at also how to handle concentration gradient, and then we will also derive relationship for the Fick's law in the next lecture. Thank you very much.